Okay, so welcome all to our second side event today at the Cryosphere Pavilion. We'll be continuing on our theme, focusing on permafrost. And so this presentation will be on slow onset high impact, what permafrost thaw, erosions, fires, and flooding means for the global 1.5 degrees Celsius target. And first up, we have speaking is Jennifer Watts from Woodwell Climate Research Center.
Okay, so can you hear me? Let me know if I'm not loud enough. So I think the order of operations is I'll give a quick introduction to the permafrost region, what's happening far north, why we should care for global carbon budgets. We'll be followed by Elton Jafrov. We'll have Fabian, and then or Gustav, and then Fabian. Something like that order. Okay, so thank you for being here. Where I'll be talking about the Arctic Boreal Zone, the ABZ permafrost region. This is 18.7 million square kilometers, almost 25% of the Northern Hemisphere's land area. And it is warming about 4 times higher than elsewhere on the planet. And unfortunately, our climate projections show that without aggressive global emission reductions, we'll continue to warm very rapidly into the future. The Arctic amplification, another term for what we call the high latitude warming, is impacted by a lot of different factors, as we see here. But today I'll be talking about one very important component, which is thawing permafrost that's releasing a lot of greenhouse gases. We have 1.5 trillion tons of organic carbon stored in soils alone at high latitudes. The carbon has been frozen in the soils, which we call permafrost, for thousands and thousands of years. However, now with Arctic warming, this carbon is being rapidly available to microbes, which are releasing the carbon in the form of CO2 and CH4 methane to the atmosphere. And this is resulting in a really horrific feedback cycle that impacts our planet and all people on Earth. So how do we track changes in Arctic boreal carbon? Well, first of all, we have satellites in space. These are detecting greenhouse gases. Most of these, except for China, has a LiDAR sensor that was launched in 2022. The rest of these rely on passive detection. They need sunlight to operate. So as long as we have sunlight, the gas sensors are scanning our Earth, detecting total carbon, total columns. And this is kind of what it looks like. This is a visualization from NASA taken late June. And we see that the red is bad. That's a lot of CO2. This is from the GOSAT-2 sensor. High latitudes in this shows quite a lot of carbon. However, this isn't the full picture. From greenhouse gases, they mix very rapidly in the atmosphere. And so with total column alone, we are unable to say where these gases came from, when they were emitted, and when they are taken back into the terrestrial and oceans through photosynthesis. To do that, we rely on other observations from in situ sensors and from models. So some of the in situ sensors include eddy covariance systems, as we see our Woodwell flux tower in Alaska, the Yukon-Kuskokwim Delta. These are able to trace gases, gas exchange, for very specific locations, and they're important because they can operate year-round, even in the frozen winter period. We also use manual flux chambers and automatic flux chambers. These sample over small areas. Sometimes if we have power, we can operate continuously, as we see on the left. Other times we rely on manual chamber measurements that are very limited in time and space. This map shows the locations of our greenhouse gas fluxes for the high latitudes. And whenever possible, so these are manned by many scientists from many nations. Whenever possible, we upload these onto repositories and make them open source. FluxNet is one option for flux towers. And then we also have the Arctic Boreal Flux database, ABC Flux is now available. And we have a version 2 coming online that includes methane and aquatic. So this information is needed for models, very important. And it also is our way to detect where emissions are coming from. So our observations are not enough. Ultimately, what we need are model systems. On the right, or let's start with the left. On the left, we have surface observations. We ingest these into models, including AI, or machine learning or process models. So we use these observations to train the models. The models then provide estimates of greenhouse gas flux, including emissions, over very specific land areas. On the other side, we have the top-down approach. This is the opposite. This starts from space or air observations. It uses a really complex atmospheric transport and chemistry models. And in the end, it gives our approximation an estimate of greenhouse gas flux. But these are over much larger areas, hundreds of kilometers even. As scientists, we really need both sides. We need to look at both because it's a way for us to help resolve and understand what the big story is, how much emissions we have over these large areas. So Gustav Galeas led a very recent paper from a recap 2. This was an international project trying to understand and quantify the current state of carbon emissions. We'll be hearing more about that from other speakers. But I want to highlight what we found here is looking at both those top-down and bottom-up model approaches. We have for CO2 a very wide range of estimates, all the way from a net sink over the Arctic Boreal zone of about 500 teragrams of carbon per year. On the bottom-up side, and that's from top-down, on the bottom-up side, we have 43, so that's indicating a net source instead of that net sink. For methane, we have much more agreement in the 20 to 44 teragrams of carbon range. And then have a look at this paper. It's very nicely describes all the attribution where these sources and sinks are coming from. We find that most of these models tell us that that net sink is driven by boreal forests. The boreal forests are incredibly important for having a sink in the area. The emissions, however, are primarily from wildfire, from rapidly thawing permafrost, and from carbon from water sources. So that said, the Arctic is changing so rapidly that it's really difficult for us to keep up with it. We are unable at the moment, using our models and measurements, to fully quantify all the emissions coming from thawing permafrost, including the thaw region in North Slope of Alaska. This situation is made much worse by wildfires, which are also increasing across the area. They are emitting a lot of greenhouse gases, and they're also destroying the boreal forests that are deriving the last amount of carbon uptake. Model estimates are showing that without aggressive reduction efforts, we're looking at future emissions from this region that are going to be much larger than all the emissions from the US at present. And this is an underestimation. It'll likely be much larger than this unless we have aggressive reduction efforts. So in conclusion, the only way to really dampen this feedback cycle that threatens our planet is through emission reductions. That's the only way we can do it. Meanwhile, we, as scientists, the science community will continue to improve our models and our measurement systems to quantify the amount of carbon so we can inform our global mitigation efforts. However, more investment in long-term monitoring infrastructure and rapid detection systems is urgently needed. So with that, I'm going to hand it off to our next speaker. And Elton, I'll give you the floor.
All right. Thank you so much, Jenny. Excellent talk. Before starting my talk, I would like to note that today I'm presenting on behalf of the Permafrost Pathway, a collaborative initiative of Woodwell Climate Research Center that is dedicated to advanced scientific research and equitable solutions to permafrost thaw. So with that, I would like to continue my presentation. You already seen this figure. So you can see the gap between the low end and high end. And what we are trying to do as a part of this project is to reduce this gap and to better quantify uncertainty and to improve the overall bias that you can see in estimates. And these are the estimates by the end of this century. So this is the most recent study that's been done. It's the intercomparison project between multiple so-called permafrost-enabled models. These are terrestrial ecosystem models that have permafrost physics represented in them. And one of the things we can see, the same thing by the end of this century, we see quite a bit of spread, and we can't really say definitively, is it going to be a sink or it's going to be a source of the carbon? So this is another study that's been done by our colleague, Christina Shado, and she outlined the processes that currently we have well represented and not as well represented in the permafrost models. And you can see these processes goes from left to right, from poor to better. There's a lot of processes that we're still lacking, or it's represented but not to the full scale. And of course, those processes contribute to this bias that we currently have. So I'm just going to briefly go through this. I'm not going to focus on this too much because for the purpose of time, I'll just say one thing we know for sure, that this process of permafrost warming is continuing and going to continue at higher speed, at higher rate. So we really want to focus on trying to quantify that. And again, I'm going to reiterate to reduce overall uncertainty. So what is the Permafrost Pathway? Permafrost Pathway is a project that consists of multiple sort of teams within the project. So we have a team who is responsible to monitor the system, to install the flux towers, and to continuously support them. We have a modeling team that I'm leading this effort on the modeling side with my colleague from University of Alaska, Fairbanks, Hélène Genet. So I should say it's a collaborative project, not just between us and University of Alaska Fairbanks, but also with other organizations. Then we have an adaptation team, and we have a policy team. But all these teams are working to better address the issue of the permafrost thaw. So in a nutshell, and this is something that, sorry, the slide a little bit shifted, but this is something that Jenny mentioned. We're trying to figure out, is the system becoming a sink? Is it becoming a source? Which system is going to change with time? And overall, basically trying to better quantify the terrestrial ecosystems. So here is the coverage that we started initially, and we've been complementing to the growing number of flux tower stations. And here in the circles, you can see the areas that not so well represented. So one of the efforts that our monitoring team is trying to accomplish is to basically have a better coverage. And we did the we ran the statistical models, and we figured that we need to add this station in the strategic locations to overall increase the coverage of the flux stations in general. And it's been more or less successful in Northern Hemisphere, in North America, and Europe has a good coverage. Unfortunately, the big part of it is the Russian Federation, and we still have lacking a good coverage over there. Hopefully, in the future, we can improve that. And you guys already seen this slide. So we are working constantly on a data set. We are working on improving carbon and methane data sets specifically for the Northern Hemisphere. And here I'm showing the difference between the version 1 and version 2. So you can see for version 2, we have much more data. Now we have methane data. So we're using all this data to upscale the fluxes from Northern Hemisphere, so-called bottom-up approach. And the other thing that we're finding is that if we incorporate the effect of fires, then one thing that we see, our numbers are shifting more towards more neutral or towards the source as opposed to sink, as we used to think about this boreal ecosystem. So here is the three type of plots that I want to present here. Is like one is the one done as a result of upscaling, then as a result of inversion. So we're looking from the satellite and doing the sort of the top-down approach. And the one that's on the right, it's from the models. And you can see that from the CMIP6 models, we would think that the system is mainly a sink, which is what when we're looking at other two plots, we see that that's not really the case. And in general, it's like more than 30% of the land now, it seems like it's actually a source rather than sink. So what we're doing in this project, we're trying to address that through the modeling effort. And I already talked about monitoring effort. And in modeling effort, the way we're trying to do it, we're trying to introduce the data simulation to do the better corrections with the actual observations. And then we're trying to add the process that we know contribute to the to changing the system from sink to source. And it's two factors that we identified we're going after is the forest fires and the thermokarst or abrupt thaw. And I'm going to quickly jump on this one. So basically, here's where we are at the moment, the estimate from the IPCC. When we add a gradual thaw and when we introduce now fires and other disturbances. And you can see that the actual effect would be triple. And in this case, we run really quick sort of reduce order model, an emulator model, just to have a better idea on where we're going with this effort. So with that, again, I'm just going to go through the highlights. And the highlights are that we need to improve and constantly enrich our greenhouse monitoring and information systems. The data sharing should be improved. So funding for the development of the Earth system model so that we have a better permafrost representation in Earth system models. And of course, inclusion to the IPCC AR5 cycle, inclusion of the permafrost and permafrost-related processes. So yeah, with that, thank you so much. I think, yeah, that's all. Thank you. And I'm going to introduce our next speaker, Fabian. Fabian, please.
Yeah, thank you very much, and welcome to my presentation. My name is Fabian Seemann, and I'm a PhD candidate at the Alfred Wegener Institute in Potsdam, Germany. My talk is about subsea and coastal permafrost environments in a warming climate. As we've already learned, the Arctic is warming faster than the global average. Since 1979, the Arctic has warmed nearly 4 times the rate of the global average. As a consequence, permafrost is warming. What is less known is that there is also subsea permafrost, and this domain also contains large amounts of organic carbon. So this means there is permafrost beneath the sea in the Arctic Ocean. And often overlooked are also the Arctic shorelines, coastlines, which are very sensitive to climatic changes. Thus, the aim of my talk is to increase the understanding of subsea and coastal permafrost environments by explaining the subsea permafrost distribution, its carbon pool, and potential of release. Also, I'm going to highlight the coastal permafrost processes and implications for organic carbon. To better understand why we have subsea permafrost, we have to look back in time. About 25,000 years ago, during the last ice age, Eurasia and North America were covered by large ice sheets. This leveled the sea levels to about 125 meters compared to today's sea level, and it exposed the last Arctic shelves, which are marked with the arrow here, north of today's coastline in Russia, and also the land bridge Varingia between Siberia and Alaska was exposed. Today, the Arctic, the permafrost region in the northern hemisphere covers about 22% of land, but also 2.4 million square kilometers of subsea permafrost remain. And the Arctic Ocean is characterized by 34% of the world's coastlines, marked by the arrow here again, the subsea permafrost distribution. And you've also already learned that the terrestrial carbon pool is very large. This is shown here in the green colors. So permafrost sort of acts as a big freezer. Plant and animal remains have accumulated here over millennia, and are locked frozen into the ground. The blue colors show the subsea permafrost carbon distribution. When permafrost thaws, microbial activity starts and starts to decompose the organic material, producing greenhouse gases. In the subsea environment, this can also occur at minus temperatures due to the salt concentration when the sediments are not actually frozen. And I would like to put this a little bit into perspective, how much greenhouse gases are actually being produced and emitted to the atmosphere. So in this bar plot, you can see countries' emission projected until the year 2100 based on their 2019 emissions. On a low emission scenario, permafrost thaw is expected to cause 55 gigatons of carbon emissions. On a high emission scenario, permafrost is causing up to 232 gigatons of emissions. This is somewhere in the range between the country's emission by the US and China. And the carbon budget that is left for staying within 1.5 degrees global warming is 250 gigatons of carbon, which shows that permafrost thaw is already contributing largely to this carbon budget. For this assessment, a subsea permafrost carbon pool of 560 gigatons was estimated by an expert assessment. I would like to present you some new numbers to that. So in these bubbles, you can see the carbon pool of different spheres. So the atmosphere, for example, stores about 880 gigatons of carbon. In the orange colors, you can see the terrestrial global permafrost region carbon pool, which is almost already twice as large as the atmospheric carbon pool. And in a light blue bubble, you can see the subsea pool with 2,800 gigatons of carbon, which is based on numerical modeling, so a much larger pool than previously expected. Subsea permafrost is characterized by slow warming, and the regulating factor for that is the sea ice distribution, as it regulates the ocean warming. As the sea ice continues to retreat, there's a risk that there will be an acceleration of subsea permafrost thaw. But currently, the emissions from subsea permafrost are at 0.05 gigatons of carbon per year. So in comparison to the expected emissions by permafrost thaw, we can expect that these emissions are actually on a higher end scenario here. But next to the subsea carbon pool, there are also gas hydrates in the Arctic Ocean. These contain a minimum amount of 20 gigatons of carbon, and this is basically frozen methane, which is here either locked in the subsea permafrost or beneath it. So the permafrost sort of acts as a lid here. And as permafrost is thawing, there's a risk for the release of these gas hydrates to the atmosphere. So this is a permafrost associated process which takes place here. And this can potentially also increase the carbon emissions that are associated with permafrost thaw. Moving to the coastlines of the Arctic Ocean. This is really the interface between the subsea environment and the terrestrial environment. And there are mainly two different kinds of coastlines in the Arctic. These are coastlines with bedrock, such as in Greenland, where there are mountain ranges along the coast, and unlithified coastlines, basically frozen sediment clasts, which hold together the coast. And therefore, also these erosions are very prone to erosion. Today, there's already an erosion rate of about 1 meter per year. And these erosion rates can even be up to 25 meters per year. But as permafrost is thawing, air temperatures are rising, sea levels are rising, sea ice is retreating, and the ocean is warming, as well as storms are intensifying. The erosion rate along the Arctic coastline is expected to increase 2 to 3-fold until the year 2100. Now the question is, what implications does this have for the carbon emissions with permafrost thaw? So the material that is being eroded into the ocean from coastal shoreline erosion is entering the Arctic Ocean. And the Arctic Ocean has a natural capacity of having dissolved carbon dioxide taking up from the atmosphere. But as additional material is entering the Arctic Ocean, this potential uptake of atmospheric CO2 is being reduced. And this is what is shown here in this graph. Somewhere between 7 and 14%, depending on the warming scenario, the atmospheric CO2 uptake by the Arctic Ocean is declining until 2100. So this is again, like with the gas hydrates, a permafrost-associated process that is relevant for the atmospheric carbon balance. To my conclusions. Permafrost is thawing and mobilizing all carbon. On this graph, you can see from the IPCC 2019 report that the near permafrost area is expected to decrease somewhere between 25 to 75% until the year 2100, depending on the warming scenario. The comparison with the emissions from industrial nations has shown that permafrost emissions are on a similar range. But there are also processes that are related to permafrost thaw that are not yet accounted for in these emission scenarios of permafrost thaw. And the comparison with the 1.5 degrees global warming remaining carbon pool shows that there is no room for additional anthropogenic carbon emissions. Every ton of CO2 that is less emitted to the atmosphere is slowing down climate change and limiting it. And with that, I'd like to come to the end of my presentation. Thank you very much, and happy to answer any questions. Okay, so I will hand over to Gustav Fogelius now from Stockholm University and the Bolin Center.
Thank you very much. So I'll run through some. There were some extra slides there that I'm just going to whiz through. Sorry. Yes, so thank you for that. So I'm going to do a little bit of a sort of overview summary talk, quite short, and then we'll take questions to all of the speakers up here and have a bit of a panel to wrap up the session. Okay, so slow onset, high impact. Permafrost thaw and the 1.5 degree target. You've already heard quite a lot of different concerning news about, or sort of findings about the permafrost carbon feedback, and I'm going to try to summarize it a little bit and give a bit of an overview. So this graph just shows you, if you squint, you can see how sort of the change in permafrost extent that we've seen in the last 20 years. So this jumps between 2001 and 2021. And this is basically observationally driven models that use land surface temperature coupled to permafrost measurements, satellite data into a model, and then you see how the permafrost boundary is already creeping northwards. This isn't the full picture because I mean here we see where we are really losing permafrost. But it's also important to remember that across the whole region, the permafrost is also warming at the same time. So you see a lot of surface changes happening also in these dark blue areas. But I think this is, to me at least, I think this is one of the really state-of-the-art products showing high resolution modeling in not quite real time, but very sort of updatable data on permafrost extent, driven by a range of different data sets, a lot of it remotely sensed from satellites and the most high-end models. But it's really like in the long process of developing this model and getting it to work really well as it's doing, it actually also relies so much on the ground or in the ground observations. So I just want to show an example of the long-term data sets that we have in the permafrost community and community working with it. This is boreholes that have been drilled into permafrost that have been there in a lot of cases for decades and decades and decades, and the very sort of unequivocal pattern of warming that we see in some of these boreholes. The filled circles on the maps shows the examples of the boreholes all across the north, and they're all warming, and it's going quite rapidly. So it's not just along the southern margins that we're losing permafrost, but also the coldest permafrost is warming actually very rapidly, leading to changes all across this region. And we've already seen this, Edson showed this briefly, but I just want to mention that in the last IPCC assessment report, there was actually the strongest language we've seen so far, I would say, on permafrost thaw. High confidence that that warming is driving it. It will lead to more carbon release. Some permafrost regions already net sources of carbon. New papers are showing that's exactly a lot larger regions are net sources than we thought. And that this is irreversible. They say centennial timescales. I would actually say century timescales is more correct. And they also conclude that the permafrost carbon remains incompletely or not at all included in almost all of the global scale models that went into CMIP6. So now we're looking to the next generation of IPCC models and hoping that the 7th generation will have these processes better included. But another thing that the IPCC did that was also the first time around is that they actually quantified the permafrost carbon feedback, not based on models, but based on data-driven evidence. So here you see, this is a graph that shows for a couple of different degrees of global warming, 1.5, 2, and 4. This shows the cumulative total release until 2100 as estimated by the IPCC. And then we land somewhere slightly below 200 or approaching 400 total gigatons of CO2 from permafrost. In this case, it's related to the full remaining budget for 1.5 degrees at the time of the 1.5 degree special report. There it was estimated to 500 gigatons. Now it's unfortunately already a lot less. But you see that this is already eating quite a lot into that budget. But there are processes that are not included there. So local scale tipping points or abrupt thaw processes. This is basically where you have massive ground ice in the soil. And when that melts and drains away, you get a successive collapse of the ground surface, leading to usually a really wet post-thaw environment that's a strong source of either CO2 or methane, depending a little bit on how wet it is and what type of environment that you're in. And this is something that we have relatively good maps, so we know which regions are vulnerable to different types of thaw. This is an example from, this is a slightly more, it's a detailed map from the recently published Permafrost Atlas. We don't need to get into details, but it shows areas vulnerable to abrupt thaw in orange and areas vulnerable mainly to gradual thaw in blue. And then the stronger the colors are, the more carbon we have stored in these soils. So you see there are some real hotspot regions that are strong colors vulnerable to abrupt thaw. And the picture is similar if we go to the Eurasian Arctic. I'm only showing the North American Arctic. And another thing that we, of course, have to factor in now, perhaps more than ever, is the overshoot trajectories that we might be heading into. So overshoot warming is, of course, when we go past our target temperature and then use some sort of negative emission technologies or whatever it might be to try to pull our emissions back down. And this is not something that is very compatible with sustainable pathways for permafrost or the cryosphere in general. Because what ends up happening, if we talk about permafrost, we have two very succinct problems with this. The first problem is that because the permafrost carbon feedback is stronger than projected, it actually drives even further warming and we overshoot even more. So we're not even at the bad red line, we're at an even worse pink shaded area there. And the second problem is that all of the damage that we're doing to the permafrost system while we're in overshoot, that's actually irreversible. It's not going to refreeze when the temperature goes back down because we changed the topography, we changed the wetness, a lot of it is going to stay thawed, and it's going to keep emitting CO2 and methane for several hundred years. So if you factor in both the abrupt thaw and the overshoot, we're actually looking at a lot higher numbers compared to the IPCC estimates. So here you have the axes are the same, except that on the far right we don't actually have a 4-degree scenario. But here you see how much additional warming the best current available science is projecting on top of what the IPCC projected. And we're hoping that this will be reflected in AR7. And then a question asked by the IPCC or the last IPCC report is that can climate change be reversed by removing carbon dioxide from the atmosphere? Here you see another example of an overshoot scenario. And if we're looking at global surface temperature change, the answer is yes, it can probably, but there's a lag time of a few years. For permafrost, they also say it can partly be reversed. That is the extent of permafrost the loss can partly be reversed. They cite a lag time of decades. I think this is too quick, actually. Most models tend to have too quick shifts in the permafrost extent, so it should probably more be like centuries. But still, the permafrost loss is partly reversible, not fully. And for some other processes, it's not reversible at a meaningful timescale. Here we see ocean thermal expansion. It's not reversible. Ocean acidification, another example, not reversible. So this is also obviously very concerning. But I actually want to go back to the one on permafrost and say that, okay, so we say it's reversible, but you will note that we've lost about, 6 million square kilometers of permafrost between these two scenarios. And those 6 million square kilometers of permafrost, they will keep emitting CO2 and methane for several hundred years. So even though it's partly reversible, we're creating a problem for the coming 7, 8, 9, 10 generations of humans to have to deal with this. So this graph shows our best projections that even if we cap warming, we stop warming at 2100, which is the sort of the dots on the left. The permafrost that thawed will keep emitting at least 2300, and it will be very high emissions. So we are really locking ourselves into future generations having to deal with these emissions with some negative emissions technology, however that's going to be solved. I don't want to guess what that would be. And this is obviously a concern. So just summarizing the impacts, the region is already a net source of greenhouse gases. That is really also affecting short-term mitigations in the coming decades. And if we look at mid to long-term, 2050 onwards, we are really committed to profound permafrost impacts. Now we only talked about emissions, but there are of course profound impacts for the people living in the Arctic and for ecosystems in the Arctic. There will be a separate dedicated session on that later this afternoon. Abrupt thaw processes create local scale, irreversible tipping points that transform ecosystems. And overshoot warming will trigger irreversible thaw that drives warming for several centuries even after the climate stabilizes. So that's sort of And global warming is reversible by removing CO2, but a lot of the feedbacks are not. So the damage we do is not reversible. So those were sort of all of the things. So thank you for listening, but actually we'll move into a bit of a question session if there are any questions. I also want to just highlight that we will have some more talks in this pavilion during the afternoon. So you can look at those titles while I ask our speakers to come up, and you want to sit up front, and we can see if there are any questions from the audience. Is this microphone on? I think you can see things. I was not. Do you have any questions from the audience? Otherwise, I guess I have a few.
I have one question about flux metering points. I saw a map there, and there were some I'm not a scientist, I'm not a professional, but it seems that there are some gaps in some territories which are not covered with these points. So do you think, as a scientist, are there enough flux measuring points? If not enough, then what kind of gaps we have? I would like to mention your comment about lack of communication with the Russian side about no information from Siberia and from Russian Arctic. Do you think it's lack of communication or lack of flux measuring points in Russia?
Yeah, so I guess I think you two are well placed to answer that question. Yeah.
I can start with the big picture. So the question is, based on the maps we presented that show the current state of our flux monitoring stations, and many of them are not long-term stations, to reflect the general funding structure where you have a 3 to 5 year period, you implement, you monitor, and then you may have to pull your tower out. So I like to say long-term monitoring, but in fact what we show on the maps is not always long-term. So that's the first thing to consider. As well as far as representation for the CO2 side of things, through permafrost pathways and our colleagues, we have strategically identified gaps in representation of ecosystem types for the entire Arctic boreal region. We recognize that some locations are so remote and very difficult to access, and it's just not practical from a bottom-up perspective to implement, to bring a structure out there and monitor. So we're targeting the areas we can actually go and deploy systems, and we've made a lot of progress. What we're missing in terms of CO2 is having greenhouse gas monitoring at abrupt thaw and recently burned ecosystems. We don't have a lot of information from those systems, and that's an area we really need to target in the future, especially to inform models. For methane, we don't have as much information currently relative to CO2, and it's difficult. In wet systems, how do you get a flux tower out in the middle of the lake? There's certain specialists that are good at that, but it takes a lot more effort. So I'm going to hand it over to Elton to talk about the issues with the geopolitical situation.
Yeah, that's a good question. Is it communication or it's actually lack of the stations? It's both. But like we actually at this scope, we participated at the flux, really good flux session organized by our Russian colleagues, and it looks like there's actually much more stations than we knew about. So now we know that there's more stations, and there is actually an effort from the Russian government to install more stations because they have to monitor, and there's an incentive there from the Russian side. With the geopolitical situation, because after the war, initially we were in a collaboration, and we're still in collaboration with our Russian colleagues, but the situation made it worse with the delivering of the stations to them, and we've been trying to find ways, but so far it hasn't been really working. So hopefully in the future the situation will improve and we could provide more stations to them, because without covering Russia, we're missing a huge part of the picture, and we really have to close that gap and close it as soon as possible. And of course, we all really want to, make progress in that direction as soon as possible. Again, I want to stress as soon as possible. I guess the situation right now at the moment, it is what it is. But I'm hopeful because after this, we hopefully will start communicating with them better, and hopefully there'll be more communication and data sharing, and those gaps that we currently have will be fulfilled. As Jenny mentioned, it's really also a logistical problem. It's really hard to put those stations in the specific locations, especially in Siberia, especially in wetlands, especially in areas when there is no roads. And most of the Russia is kind of really hard to pick like. So yeah, thank you so much.
But I again want to emphasize that climate change stops for no one, right? It's happening now. It's going to get worse. It's impacting all of us. Science should never stop at political borders. And this is an area where we really need our leadership, our global leaders, to step up and let the scientists, let policymakers do our work.
Are there any thanks for that question? Any other questions? But actually, I would just like to. Fabian, you're working on the coast and on the subsea system. Do you want to comment a little bit on the data availability and sort of limitations and like what are the biggest hurdles for improving the observational base for the subsea and the coastal environment? Do you have a sense of this?
Yeah, so the subsea environment definitely comes with uncertainties because it's so hard to access the subsea permafrost. Now what I presented these numbers, like the smaller carbon pool of subsea permafrost was based on an expert assessment, not actually on quantitative data, because of a lack of actual measurements. And the other carbon pool estimate is based on numerical modeling. So there is some data input from boring, for example, that took place in the Arctic Ocean, but still the uncertainty is relatively big, I would say, in the subsea environment, and also the exact response of it. So we have an idea that there's a slow warming trend and it causes emissions, but there's definitely more research needed for especially the subsea environment.
I think it's extremely challenging to have the infrastructure in place to measure greenhouse gas fluxes over the Arctic Ocean. It's an area that's difficult to be in at the best of times. To have permanent monitoring stations are quite limited in what we are able to really monitor, and you have to rely a lot on models which have supported there. Okay, I think with that, unless there are any other questions or comments, I think we can wrap up the session and
So I have a question. What do you guys think are the odds that this new information, permafrost thaw, a possible rough thaw, wildfire emissions in the north are included in this next round of IPCC talks that they're having? What's the sense that something that people are actively considering, like adding all this data in, or is that still like a stretch?
Well, it remains to be seen, but I think that us showing up and many voices collectively delivering a message has a good chance of reaching ears.
So I guess I can just quickly repeat. I'm not sure if it's heard online, but the question was what are the chances that all of these additional processes of abrupt thaw and fire will be in the next IPCC cycle assessment. I think I would say that to have it represented in the report based on data drift, so like given their best estimate, I'm pretty confident that it will be in there. So something along the lines of the graph that I showed where we add, something along those lines, I think it will be in there. But to what extent it will be represented in the fully coupled climate models that the IPCC that they use, that is more uncertain. We have two, like in the last round, two of the models have permafrost represented at all. And the problem is not necessarily that we don't have models that have this competency of actually modeling it. I think the progress has been very rapid, but the problem is that to something like IPCC, the modeling centers, they can only send one model version usually, and then they will send their most globally stable version. And in a lot of cases, the model versions that do the best in the Arctic might not be the same as the core global version that is used for core global routes. So it's like a lot of these models, they do have a version that can model these processes much better, but it's not the one that's going to go to CNIP 7. I don't, but as you have a, you are,
Yeah, I'll just also add to it the scale. So the global model that operate on like half-degree scale, which is 150 kilometers by 150 kilometers. So the features that we're talking about is like ice wedges, which is on a meter scale, right? So the representation 150 kilometers, you won't be able to represent the smaller features. Smaller lakes and ponds, they contribute a lot in comparison to big lakes and ponds. So we really have to represent that. The wetlands contribute a lot. I mean, it's kind of complicated. It's complicated both ways. It's complicated to like implement it mathematically and then but once you have implemented into the model, then you need to make sure that all the physics that you have, between your, ground and the atmosphere preserved, and you're not, failing any of that physics. So it's actually not so easy as it sounds. That's why there is so much resilience on the modeler side to include permafrost, because they know that if we're going to include the permafrost, then the other things might be somehow be distorted, and then we have to spend so much time trying to figure that out, how to make the whole thing works, and the development takes a lot of time based on my experience. So with that all in mind, that's why we're sort of trying to push that and to raise our voice to say that we understand all the challenges, but nevertheless, we think that it's worth investing in there because we think that these small processes are super important. And if we're missing those processes, then, even though we're going to have like what I showed, we're going to have a sink which might be misleading, and they think that that's misleading.
Right. My voice is giving out a little bit here after a week. In a lot of the slides, very large uncertainty. And it seems whenever a new process comes online, where we land on the uncertainty bound is towards more adversarial outcomes. That is, it's worse, not better. I'm just curious, based on all four of you expert judgment, we are found. My gut is at the high end, as opposed to the low one.
I would have to agree. So a lot of those, like if it's a synthesis of a lot of different studies that come together, like what the IPCC did, they are quite cautious, and then a lot of these processes that add to the uncertainty, they are not really fully represented in a lot of the studies. So like the few studies that would have included all of the different processes, that would tend to be on the higher end. So I would agree that we are probably on the higher end. But then of course also the uncertainty like between, I think it's also important to remember that like the biggest, if we look at this massive range, I think it shows it really well, the biggest difference is still between the lower emission scenarios and the high emission scenarios. So like the gap between what we can say by lowering emissions relatively rapidly, that is really, really large. But sure. Then for all of the, we probably are in the higher end, I would say.
And I'll add a large source of uncertainty because we're talking about the full permafrost region, which includes the tundra, the treeless landscapes, and the boreal forests. Boreal forests are helping us mitigate whatever is coming out in the form of emission. If we lose those forests, we're rapidly into the high emission scenario like we can't even imagine.
I would also say with the permafrost associated processes, like with the gas hydrates and the CO2 in the Arctic Ocean, which is reducing the sink capacity of the Arctic Ocean, there are these processes that also show that we're probably rather on the higher end of these scenarios because we haven't accounted yet for these processes. Especially the gas hydrates, they are not yet really well understood.
I have one more if nobody else has. Yeah, sure. So on the subsea permafrost, and the thaw that is occurring there and so forth, is there some kind of equivalent to like what's happening on land? We're seeing the large wildfires on the surface. Is there some kind of process like currents or something else that could have like rapid thaw in the ocean? Is there current changes or ice I don't, is there things like that that could drive rapid thaw?
So as far as we know, it's a slow response because temperatures are still relatively stable. Like the ocean is warming and currents can change, but so far it's a slow warming response. But as I also said in the presentation, as sea ice is continuing to retreat, there could be a big acceleration of this thaw, like this thawing of the subsea environment. This is expected to occur likely after the year 2100 approximately. So there's a risk for that.
So I think there's a link between sea ice and subsea permafrost because when there's sea ice, sea ice basically creates very, very heavy water because of the brine. It excludes so the brine exclusion leads to formation of heavy water, cold water that sinks, and that would like protect the subsea permafrost. When you don't have any sea ice, that sort of triggers the warming. That's right. So there's a coupling between sea ice and permafrost that are very interesting, but not super well understood, but quite concerning. Okay, but then with that, I'll say thanks to all of you. We're back again in half an hour, so we'll have time to get some lunch.
I got some more park calls.